When we think of a black hole, we often imagine a massive cosmic drain, pulling everything into a bottomless pit. But the name is a bit of a misnomer. A black hole isn't an empty hole at all. It is a region of space where matter has been squeezed into such a tiny volume that gravity becomes overwhelmingly strong. To understand what happens at the center, we first have to discard our everyday intuition about how space and time work. In this environment, the rules we learn in school begin to bend and eventually break entirely. To grasp why black holes are so unique, we must look at Albert Einstein's view of the universe. He proposed that space and time are not separate, but woven together into a four-dimensional fabric called spacetime. Massive objects, like stars or planets, sit on this fabric and create a curve, much like a heavy ball resting on a trampoline. Usually, these curves are gentle, guiding planets into orbits. However, a black hole is what happens when a curve becomes so steep that it creates a localized pocket from which nothing can escape. Every object has what we call an escape velocity, the speed required to break free from its gravitational pull. On Earth, that speed is about 11 kilometers per second. If you were to compress the Earth down to the size of a marble, its gravity would become so concentrated that the escape velocity would exceed the speed of light. Since nothing in our universe can travel faster than light, nothing could ever leave that marble surface. This boundary, where the escape velocity matches the speed of light, is known as the event horizon. Now, imagine you are watching a friend fall toward a black hole while you stay at a safe distance. As your friend approaches the event horizon, something strange happens to your perception of them. Because gravity warps time as well as space, clocks near a black hole tick more slowly relative to yours. From your perspective, your friend's movements would begin to decelerate. Their watch would appear to crawl, and the light reflecting off them would stretch out, shifting from its natural color to a deep, faint red until it eventually disappears. This leads to one of the most counterintuitive facts in physics. From your perspective as an outside observer, your friend never actually crosses the event horizon. You would see them get closer and closer, moving slower and slower, eventually appearing to freeze at the very edge. This is why some early physicists referred to black holes as frozen stars. To the rest of the universe, the information of your friend's presence is permanently etched onto the horizon, never quite falling in, while their image slowly fades into the infrared darkness. However, your friend's experience would be completely different. They wouldn't feel time slowing down at all. As they drift toward the event horizon, they would look back at you and the rest of the universe. Because of the extreme time dilation, they would see the entire history of the cosmos speed up. Stars would flicker out and galaxies would collide in what feels like seconds. To the traveler, they are falling into a hole, but they are also witnessing the distant future of the universe unfold in a blinding flash of light. Once the traveler crosses the event horizon, the very geometry of the universe swaps places. In our daily lives, we can choose to move left or right, forward or backward, but we cannot choose to move backward in time. Inside a black hole, the radial direction toward the center becomes time-like. This means that the center is no longer a place in space, but a moment in your future. Just as you cannot stop tomorrow from arriving, a traveler inside a black hole cannot stop themselves from moving toward the singularity at the center. As the traveler gets closer to the center, they encounter a process known as spaghettification. Gravity is much stronger at their feet than at their head because the distance to the center is so small. This difference in force, called a tidal force, would begin to stretch their body into a long, thin strand of atoms. While this sounds violent for a truly massive black hole, the event horizon is so large that a traveler might cross it without feeling anything at all, only realizing their fate as they draw closer to the singularity. At the very center lies the singularity, a point where our current understanding of physics simply stops working. According to general relativity, the density at this point becomes infinite and the volume becomes zero. But infinite is often just a word scientists use when the math breaks down. To truly understand the heart of a black hole, we would need to combine gravity with quantum mechanics, the study of the very small. Until we have a theory of quantum gravity, the singularity remains a locked door at the end of time. So, do you ever reach the center? The answer depends entirely on who's asking. To an observer watching from a telescope, you remain a frozen ghost at the edge of the horizon for eternity. To you, the traveler, you reach the center quite quickly, but only after watching the universe end behind you. Black holes remind us that reality is not a single, objective experience, but a collection of perspectives shaped by the heavy, invisible curves of the space and time we inhabit.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.